This video covers one-sample tests for quantitative data. We use these methods when there is one quantitative response variable, no explanatory variable, and we want to make an inference about either a population mean or a population variance. At a high level, one quantitative sample can lead to two common questions. We may want to test a claim about the population mean, or we may want to test a claim about the population variance. This image shows where these one-sample methods fit in the overall flow of methods for quantitative response variables. For the one-sample t-test, we begin with a random sample x, sub 1 through x sub n, from a population with mean mu. The null hypothesis compares that mean to a hypothesized value mu sub 0. The null hypothesis says mu equals mu sub 0. The alternative may say mu is not equal to mu sub 0, greater than mu sub 0, or less than mu sub 0. The main assumptions are a simple random sample independent observations and an approximately normal population, or a sample size large enough for a normal approximation to work well. The test statistic is t equals x bar minus mu sub 0 divided by s over the square root of n. Under the null hypothesis, that statistic follows a t distribution with n minus 1 degrees of freedom. The p-value depends on the form of the alternative hypothesis. We can also build a confidence interval for mu, using x bar plus or minus a critical t-value times s over the square root of n. In example 1, a botanist measures the nitrogen content of 15 leaves. The sample mean is 3.4, the sample standard deviation is 0.6, and we test whether the population mean differs from 3.0. Plugging into the formula gives a t-statistic of about 2.58 with 14 degrees of freedom. The p-value is about 0.021, so we reject h sub 0 and conclude the mean nitrogen content differs from 3.0. We can also test a claim about a population variance. In that setting, s squared is the sample variance and sigma squared sub 0 is the hypothesized population variance. The null hypothesis says sigma squared equals sigma squared sub 0. The test statistic is chi-square equals the quantity nn minus 1 times s squared divided by sigma squared sub 0. This uses a chi-square distribution with n minus 1 degrees of freedom. A confidence interval for the variance is built using chi-square critical values. If we take square roots of the endpoints, we get a confidence interval for the population standard deviation. In example 2, a company targets a variance of 0.04, but a sample of 25 springs has a sample variance of 0.065. We test whether the true variance differs from the target. The chi-square statistic is 39.0 with 24 degrees of freedom. The two-sided p-value is about 0.055, so we fail to reject h sub 0 and do not find a significant difference from the target variance. The main takeaways are that the one-sample t-test is for a single population mean, the chi-square method is for a single population variance, and both methods should be paired with a confidence interval, as well as a hypothesis test conclusion.